All right, in this video, we're going to talk about the Lagrange error bound. And what it's going to do is it's going to tell us how close our approximation using a Taylor polynomial or Maclaurin polynomial is to the actual solution. So this might be a video that you're watching after we've done the lesson already, just to maybe kind of brush up on or try to understand better. And that's why I'm making it. So the exact value, if we're talking about a function, so remember, we're trying to use these Taylor polynomials to approximate functions like sine, cosine, natural log. So the exact value would be f of x. The approximation is our Taylor polynomial, we'll call it p of x, plus the remainder, which is going to be r of x. And hopefully that kind of makes sense. So the approximation plus the remainder, that's going to be your exact value, and your remainder could be negative. So the difference between our approximation, that's it. So the error, if I solve this for r of x, so r sub n of x, we'll call it, would be, if I subtract p of x from both sides, is going to be the absolute difference of the original function and the Taylor polynomial of nth degree. And hopefully that kind of makes sense. The remainder is just the difference between the actual function and the approximation. So I'm gonna write a little note. This is the actual value. This is the approximation. The difference in those two is our error, and we want to find an error bound for this. So our actual number, I'm going to write it down here. Our actual function value, this is the actual value, that is equal to our approximation. So this right here, that's your Taylor polynomial, right? That's how you write a Taylor series. So this is the approximation plus the remainder, which is what we just wrote a second ago, right? Remainder. So what is the remainder? The remainder is the next term, we're going to call it in the series. So here's your Taylor polynomial, f of c, plus the first derivative evaluated at c times x minus c, and just how we built the Taylor polynomials in the last lesson. The actual value is just whatever the Taylor polynomial approximation is plus the remainder. And we're going to think of the remainder like the next term. The next term, if I start, like this would be the nth term. The next term would be the derivative to the n plus 1 term. I'll write it below. That is going to be the nth derivative plus 1 evaluated at c times x minus c over n plus 1 all over n plus 1 factorial. And that's just the next term in the Taylor polynomial. And so what we're going to do is this would be equal to the remainder exactly. But this derivative, instead of finding out what it is at c, what we're going to do is basically find what is the maximum value. What is the max of that derivative of the n plus first derivative evaluated at z, where z is any number between x and c, times x minus c of n plus 1 all over n plus 1 factorial. So what this is saying is we're going to look at the very largest thing that this term right here can be, this n plus 1 derivative evaluated at some number. Instead of the center, we're going to say, what's the biggest it could be all together? So for any value of z in between our x and c, for anything, what's the biggest? Then we know that's the absolute biggest this whole thing can be. So our error would be less than or equal to that. And that might have made sense, it might have made no sense. But it says, let f of x be differentiable through the order of n plus 1. The error between the Taylor polynomial, which is the approximation, and the actual value of f of x is bounded by, and we're going to say it's the absolute value, of the absolute biggest term of the n plus 1 derivative. We're just going to call that z, but it's just, think of the biggest, times x minus c, the rest of that normal polynomial, but it's the next term, so it's the n plus 1. over n plus 1 factorial. All right, so if I'm trying to find the remainder using like a third degree Taylor polynomial, the n would be 3, so over here I'd plug in 3, this would be the fourth derivative. That would give us that next term in the Taylor polynomial. All right, so let's see how this kind of works. Let's do an example, maybe make more sense. It says the fourth degree Taylor polynomial for cosine of x is given by p sub 4 of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. If this polynomial is used to approximate cosine, should be one of them, cosine of 0.2, what is the Lagrange error bound? And just think of it as like the next term. Just like in the alternating series, error bound is always less than the next term. This would be the next term in the Taylor polynomial. So it's a fourth degree Maclaurin polynomial, means c is 0. It's centered around 0. So just so you know, cosine of 0.2 in the calculator is about 0.980067. That's in the calculator. No, it's not. Let me see. Cosine of 0.2 in the calculator is 0.9800665778. If I plugged it into the Taylor polynomial, so I'm going to say, this is just kind of extra. So this is actually f of x. F of 0.2 is equal to that. Okay, plug into the Taylor polynomial, I get 1 minus, what would that be, 0.2 squared. Doing this right now in the calculator. Plus 0.2 to the fourth over 4. The Taylor polynomial approximation is equal to 0.9800, and then it's 6666667. So pretty close using a fourth degree Taylor polynomial, but what we're trying to find is how much is it off by? What is the error bound? So the error bound, r sub 4, an absolute value of x, is going to be less than or equal to the maximum of the fifth derivative evaluated at z of, and then times, what would that be? X is 0.2. I'm just going to say x for now. I'll plug in my numbers in the next step. X minus 0, because c is 0, to the fifth power all over 5 factorial. And what this would be equal to, okay, what is the fifth derivative of our function f? So f is cosine, right? Cosine of x, what am I writing? F of x is equal to cosine x. So f prime is equal to negative sine x. The second derivative is equal to negative cosine of x. Third derivative is equal to sine x. Fourth derivative is equal to cosine of x. Fifth derivative is negative sine x. All right, so that's the one I need to find, because in my Lagrange error bound, I want to know what is the absolute biggest that the fifth derivative, oh, this is bad notation, I should say equals. The fifth derivative of x is equal to negative sine of x. So what is the biggest this could be? What's the absolute biggest it could be? Because if I use the biggest there, the actual value of the fifth derivative would be either less than or greater than that. So we're taking into account that we got the biggest. So in this case, I don't know all the function values of x. So the z has to be between 0 and 0.2, but I don't know those values. So when I see sine and cosine, I'm just going to put the maximum is 1. Because on my unit circle, the biggest x, the biggest y is always 1. So I'm going to say the maximum fifth derivative is just 1. Times 0.2 to the fifth power over 5 factorial. The 0.2 came from plugging in the 0.2 for x. So this would be equal to, just plug it to the calculator, it's like 0.000002667. And what this is saying is, if I used a Taylor polynomial of fourth degree, which was given, to approximate the value of cosine of 0.2, that approximation is within this much of the actual value that we can get using our calculator now. All right, that's a lot. So let's do another one. Hopefully it makes more sense as we go. So it says, use a third degree Taylor polynomial in the interval 0 to 1 for e to the x centered around x equals 0, so it's a Maclaurin polynomial, to approximate e to the first power. Okay, we know e is that 2.72, blah, 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 that number that goes on forever, right? All right, what we want to do is build a third degree Taylor polynomial and use that to approximate what that value is at 1. And then we're going to use Lagrange error bound. The Lagrange error bound is used for Taylor polynomial approximations. The alternating series error bound is used for alternating series to see how close those are. So let's build our third degree Taylor polynomial. So I'm right, p sub 3 of x is equal to f of 0, because it's a Maclaurin polynomial, plus the first derivative evaluated at 0 times x, plus the second derivative of 0 times x squared over 2 factorial, or just 2, plus the third derivative evaluated at 0 times x cubed over 3 factorial. All right, so to do that, we need f of x is equal to e to the x. F of 0 is 1. The derivative of that is equal to, well, e to the x, so f prime at 0 is also equal to 1. So those are all going to be equal to 1, right? So when I'm building this out, and we're going to find the shortcuts here pretty soon, p sub 3 of x is equal to 1 plus 1x plus 1x squared over 2 plus 1x cubed over 3 factorial. So p, the third degree Taylor polynomial evaluated at 1, it's going to approximate, we 1 plus 1 plus 1 half plus 1 over 6, which is 2.666666 repeating. Oops, where'd it go? So I'm going to just say it's 2.6 repeating. All right, so that's our approximation using a third degree Taylor polynomial, or Maclaurin polynomial, since it's around 0, to approximate e of 1. So if I want to find the error bound, so I'm going to say the error bound, the absolute value of r of 3, because we could be too high or we could be too low. So the difference, the error could be positive or negative. So I'm saying the absolute value, just how far off I, is less than or equal to the absolute value of the max, the highest number, the highest value that the fourth derivative evaluated at z is, times x to the fourth over 4 factorial. So it's just the next term. So third degree Taylor polynomial, you plug in 4 for the ends, because n plus 1, next one. Okay, so again, what this does is the derivative evaluated at 4 anywhere in between 0 and 1. So it's in between where we're centered and the value that we're actually trying to find. We're going to say the absolute biggest number that is, because it could be anything in between there, right? But we're going to say, well, let's just take care of, let's make sure we get the absolute biggest out of that, and then our error would be less than that. So this would be equal to, okay, the fourth derivative, we just taken the derivatives, and the fourth derivative is what e to the x. So what is the highest value on the interval from 0 to 1? I know e to the x goes like this. So e to the 0 is equal to 1. E to the first power is equal to e. E is the biggest it could be. So the fourth derivative, the absolute maximum it could be would be e. Now our number that we're plugging in might actually be like smaller than that. We don't know. Times, okay, we're trying to plug in 1. So this would be 1 to the fourth power over 4 factorial, which is equal to e over 24, which is equal to 0.11326. Oh, I ran out of room. 0.1132617. So I know what this is saying is my approximation that I got, if I was to actually find out what e to the first power is, e to the first power, e is just 2.718281828. That pattern goes on. I don't know if it actually does or not. I should know more about e, I don't. But anyways, that actual value, if I plug in 1, and if I use my Taylor approximation, this approximation is going to be off by at most this error bound. That's what our error is. And if I look at it, if I add what I got, that error bound, the 0.1132617, add that to 2.6 repeating, I get 2.7799, which you can tell is more than the actual value, right? So our error is within that much. The actual number is within our possible error. We are saying this could be off by as much as 0.113. Anyways, I think I'm just saying the same thing over and over and over again. It might not be making sense. All right, one more. Actually, we're gonna pause this video and we'll do the rest on a separate video. So hopefully this helped. Thanks for watching and bye.